Our exam one, our first exam, is 1 week from yesterday. 7 p.m. in Follinger and 2 rooms in Gregg Hall. I'll email you your room assignments as soon as people have finished signing up for the conflict. Now, anybody who wants to can sign up for the conflict. You don't need a reason. You might just like to take an exam earlier. Fine. The conflict's no harder or easier, just a slightly different version, and you can just sign up on Lon Kappa. But please do that by midnight Friday. Okay, Friday at 11:59 p.m. That way we have so many people to organize that we can get you all set up and get your room assignments taken care of. So just go there and sign up. Any questions on that? Yes?
Can we use graphing calculators?
You may use whatever type of calculator you want on the exam, which brings me, thank you for asking that question. Because here we left off on page 34, and we just calculated a standard deviation for a list of numbers. So you will have to do that on the exam, and so her question is very pertinent because if you have a graphing calculator and you know how to do that, you can just put that list in and it will calculate for you a standard deviation. So, can you use that? Sure, you can use that, but don't run out and get one of these calculators if you don't already have one, because it's not really going to help you very much, if at all. For one thing, you have to show your work. So you're going to have, why is there that noise? That's not us, is it? Who is that? Is that us? Was that us? Okay, this is much better, much better. Okay, so if you bring your graphing calculator, you may use it. It could compute a standard deviation. But you're going to have to show all your work anyways. And if you just wrote down the answer like this, you wouldn't get any credit. Now, the other thing is you might write down the wrong answer, because I should make a note of this. Make a note. If you do use your calculator to check after you go through all these steps and you want to check, note. What do you want to do? The SD, the standard deviation, on a calculator, what does it look like? They don't say SD. Calculator is, they'll give it a Greek letter, sigma, not S, okay? We'll learn this later. Basically, what's happening is that many of you, I'm sure, have learned how to calculate a standard deviation, but instead of dividing by the number of entries on the list, you divide by one less. Raise your hand if you've ever heard of this. You divide by n minus 1. Don't do that here. That's not, for this situation, that's the inappropriate statistic. All we're trying to do here is we have the whole population, let's say. We have the whole, we're only concerned with these 7 numbers. And so obviously, we just want to take the average here. Later on, we're going to see something else. This is a slightly bigger standard deviation, and what it really is an estimate of a larger population. If you randomly took these 6 numbers, these 7 numbers, 1, 2, 3, 4, 5, 7 numbers, out of a much larger population, and you wanted to estimate the standard deviation of that larger population based only on this sample of 6, well, then it wouldn't be a great estimate. This wouldn't. So we adjust it somehow. We adjust it and we have a little more uncertainty, and we make this a little bit larger. And that is what would happen if you divided by 6 instead of 7. We're going to go into that in detail later when we get into inferential statistics. But for descriptive statistics, this is our data, and this is the correct standard deviation. And if anybody tells you anything different, they're wrong. Okay? they're measuring two different, this is correct for what we're doing. So please do this. And then, would it help you to check? Well, first thing that you'd want to do to check if you're doing your work correctly would be to add up your deviations and make sure they sum to what? What should they sum to? 0. That's your first check. If they don't sum to 0, you did your arithmetic wrong. Recalculate your average and then go back and subtract that average from every single number. You won't always get a symmetrical distribution like this, but they will always sum to 0. So make sure they sum to 0. Check that they sum to 0 there. And then, let's say you stopped right before you did the square root. Some people do that, and they just saw 4. Well, here's your deviations. If you got 4 as your answer, you'd know that would be wrong, because the very largest deviation you have is 3. So how could your typical range of the deviations be larger than the very largest one you have? If you eyeball that, it looks like, 2 would be about right. We have bigger ones and smaller ones. So if you do make a careless mistake, arithmetic mistake, we take off very little if you have your steps correct. Now, another thing we should go over, that was a good question, thank you. Another thing we should go over is here when I said that if you double every number on the original list, what's the new standard deviation? And I said the standard deviation would double. In general, if you multiply or divide by any number, the standard deviation will be multiplied or divided by that number. So it'll either stretch if the number's greater than 1 or shrink. What happens if the number's less than 1? What happens if you multiplied by -2? Here we said double, but let's say we took this original list, and instead of doubling the numbers, we multiplied each and every number by -2. Then what would we get? Well, this would be 0, but we'd get a 1. Here, 1 would end up being what? 1 would end up being, this would be 0, and then we multiply by -2, we'd get a -2, a -4. And we just go this way, a -6, -8, -10, and -12. They'd be spread out. They'd be spread out just as far, but they'd all be negatives. Now, so the standard deviation measures the spread. So what do you think the standard deviation would be? Do you think it would be 2 or -2? Raise your hand if you think it would be 2. Raise your hand if you think it would be -2. Okay, let's think about it. 2 ways. First of all, look how you calculate the standard deviation. You're taking this, doesn't look like it could ever be negative, but more importantly, what would a negative spread look like? Well, yeah. What would a negative spread look like? Doesn't it? It kind of doesn't make sense. Does it to you? I mean, do they be so close together, the numbers, that there'd be negative space in between them? It hardly makes sense, does it? The standard deviation can never be negative. So that if you did multiply by all of them by -2, the standard deviation would be doubled. The standard deviation can never be negative, all right? What do you think the smallest the standard deviation could be? What do you think the smallest number the standard deviation could be? If the numbers were so squashed together that all the numbers were the same, right? Then the numbers were all the same, what do you think the standard deviation would be? 0. It can't get any smaller than that. Now, if the standard deviation was 0, do you think all the numbers on the list would have to be 0? Right, no, he said. They could just all be the same number. If they were all 2, the average would be 2, and they would all deviate by 0 from that average. So if all the numbers are the same, there's no spread at all, and the smallest the standard deviation can be is 0. Does that make sense to everybody? All right. I think we said that. I think I said that in the summary. I just didn't emphasize it. So if you want to go to the summary and underline that, right here, it says, or highlight it. We're on page 36. So the standard deviation can never be negative. All right, this was important too. Well, it's all important. Good way when you're studying, besides doing all the practice exams, is to just familiarize yourself with all the concepts that were covered in every chapter, and that's in the summary at the end of every chapter. All right. Now, this last point we didn't go over yet, but it feeds nicely into the next chapter. So let's start the next chapter, and we can just cover that point here. So the next chapter is on the normal approximation. Have you ever heard of the normal curve or the bell-shaped curve? Raise your hand. Okay. Well, it's a curve that's really an idealized histogram. And probably the reason you've heard about it so often is because so much of data in the actual world follows, not perfectly, but resembles the normal curve. For example, in the variables that we looked at in our survey data, the age of your mothers. You wrote down how old your mothers were. Age of your fathers. Both of those seem to follow the normal curve. You know, some of you had mothers and fathers in their 60s and down here in their 30s, but most of you had them in their 50s through here. And height is another one. Weight is another one. ACT scores are designed to follow the normal curve. If you look at the whole population of ACT, any standardized tests, that's what it means when they standardize a test, is they scale them to follow the normal curve. So there's many data sets that do follow the normal curve, and there's many that do not. For example, income we saw does not follow the normal curve. It has a very long right-hand tail, and looks nothing like the normal curve. My exams don't follow the normal curve because this is a gen ed course, and I don't want them to look like this. I design them so that there's a lot of people at the high end, and then there's a few people who are going to do poorly no matter how hard I try. They're just not going to show up, they're not going to study, and so it's going to have a long left-hand tail. So my exam scores never look like the normal curve. All right, but for data sets that do resemble the normal curve, we can do something extremely useful that you're going to love, and that we're going to do throughout this course. And that is that we're going to be able to draw histograms of our data set without actually looking at all the data. All we need is just two numbers, the average and the standard deviation. And from those two numbers, we will be able to draw what I call an approximation of our histogram. It won't be our exact histogram. Remember, our exact histogram would be a series of, would be very jagged. For example, it would look like, let's turn the page here for just a minute. It would look something like this. A jagged histogram, with rectangles. But what the normal curve, we can superimpose upon that a normal curve. This isn't our own data on page 38, but what this data is data from a national survey on women's health, and one of the questions asked was, how tall are they? These women were 18 to 74. This was a few years back, and the average height was 5'3.5", That's the average, and the standard deviation was 2.5 inches. And the actual histogram is very jagged, as you've seen ours is. But do you see how we can superimpose a bell-shaped curve that approximates it fairly well? I mean, sometimes the actual histogram is a little bit higher than our approximation, and sometimes it's a little bit lower, but overall it does a fairly good job. Okay, so as I said on the previous page, the normal curve has an x-axis in standard units. Any particular data set that we look at has actual units, like if it's height, we had inches, weight, we had pounds, etc. But the normal curve is this measuring stick that would apply to any data. It has no units whatsoever. It's a ranking. And so what's the average on the normal curve is always 0. We call them standard units or z-scores. And the average is always 0, and the standard deviation is defined as just 1 unit is the standard deviation. So if we want to, for example, translate our data, which follows the normal curve first, it has to resemble it pretty much. Like, let's say our data on guys' heights. I think that follows the normal curve pretty well, and maybe the average, I'm just approximating, I think was about 5'10". Let's say it's 70 inches, and let's say the standard deviation was 3 inches, and it's pretty much like the normal curve. Well then, if we translate the x-axis from inches into standard units and get used to working with this normal curve, you'll be able to see pretty quickly what percentage of the data falls within any interval. For example, you would see that you'd see that about 68% of the men would be between 5'10", give or take 3 inches. And you could see that above, what's 3 inches above 5'10"? 6'1"? About 16% of the guys in the class are above 6'1", etc. So you're going to be able to do this in your head. It's extremely useful. So where do we begin? We begin by, first of all, changing this, whatever units we're in, into standard units. How? Well, let's look at this data here first, and I think you can get an intuitive idea right away how you would do that. The true average of these almost, 6,588 women is 5'3½". They're pretty small, but they include a lot of older women. So 5'3½". So that would line up with a z-score of 0. If you have a z-score of 0, you are exactly average. Doesn't mean you're 0 inches tall. It means you're right on the average. If you're above average in height, you will have a positive z-score. Remember, I say the normal curve has a standard deviation of 1. So note that this data has a standard deviation of 2.5. So if somebody is 1 standard deviation above average in height for this population, we would add 2.5 inches to the average, and we'd get up to 5'6", 66 inches. Well, that would line up with a z-score of 1, 1 standard deviation above the average. Similarly, if you're 1 standard deviation below the average with this data, you'd be 2.5 inches below 5'3½", which would put you at 5'1", and there your z-score would be -1, and that's +1. And on any normal curve, about 68% of the data lies between 1 and -1 standard deviations. And doesn't that look about right here? The shaded area here and the actual histogram, if you just eyeballed it, doesn't that look over 50%, like about 2/3 of the entire histogram? And between standard deviations up. If you went up 1 standard deviation is 2.5 inches. So if I went up to go up 2 standard deviations, wouldn't I go from the average, I'd go how many inches? 5. So we'd start at 5, 3.5 and go all the way to 5, 8.5. And there is 2 standard deviations. You can make a little line right there. And then if I went down 5 inches, I'd go all the way here to 58.5. That's what, 410.5. And about 95% of the population, doesn't it look like about 95%, is between -2 and 2, isn't that 5, 10.5? 5, 10.5 and 5, 8.5. This is a smaller population than you guys. But doesn't it, what I'm saying is, you don't have to color this in on your own, but all I want you to think about is that this histogram here, all this space on the actual jig-jaggedy histogram is about 95%, and it's also about 95% on the smoothed out version. So it corresponds pretty well. All right, now that is what, excuse me, let's just turn back to the first page here on 37 so I can just show you exactly, that's what I just showed you with an example. The normal curve is symmetric about 0. Its SD is 1. And the area under the curve is 100%. It actually goes on in either direction forever. The equation of the curve goes on, but there's hardly past 3 or -3, a very small percentage of the population lies. But theoretically, the equation for the curve never crosses the x-axis, okay? And so this is the 1, 2, 3 rule. What I said about approximately 68% of the data is within 1 standard deviation of the average, and approximately 95% is within 2, and then 99.7% approximately is within 3 standard deviations of the average. So just about everybody is between 3 standard deviations of the average in any bell-shaped distribution. There are people who are outliers who are further than that, you know, extreme geniuses, for example, in IQ, or really, really tall people or really, really short people, but most people are within 3. Okay, now let's go here and answer these questions. So, what do I say up here? Okay, so we intuitively looked at this and lined up how the inches corresponded with the z-scores, but here is just a simple formula that says the same thing. That a z-score, also called standard units, to find the z-score, you just see how far the value minus the average over the standard deviation. So let's do that here. And see, what is the height of 66 in standard units? In other words, how many standard deviations above average is a height of 66 inches? Well, we saw that it's 2.5 inches, which is 1 standard deviation. But if you like to prefer the formula or want to see how it relates to that, you say z equals the value, which in this case is 66 inches, that's what we're calling the value, minus our average, I got used to abbreviating it that way from the book, I hope you don't mind, over the standard deviation. So in this case, 66 inches, and our average is what? We have to look up here. Our average was right here, and there's our standard deviation, so I don't lose it. Okay, 63.5 inches, and then we're dividing by the standard deviation. So all we're really doing here is what? We're saying, okay, somebody's 5'6" is 2.5 inches above. We all know that. 2.5 inches above the average. And We just want to know how many standard deviations that is. Because these standard units tell you how many standard, so 2.5 inches is how many standard deviations. So you just divide 2.5 into 2.5, and obviously in this case you get 1. So what that means is a z-score of 1 means z equal 1 means the person is not, it's not 1 inch. There's no units here. See how the units cancel out? It's unit free. It's unit free. It means the person is not 1 inch tall or 1 inch above the average. There's no units there. It could apply to anything we're measuring. Not just height, not just weight, not anything that follows a normal curve. It means 1 what? What is that? It's 1, not 1 inch, not, what is it? 1 times what? 1 times 2.5, it's 1 standard, it's 1 standard deviation. 1 times the standard deviation. Above average. It will always mean that, no matter what distribution you're in. That's what 1 means. Okay, how about a height of 60 inches? Change that to a z-score. So what would you do? You start with 60 inches, and you'd subtract off the average, which is 3.5 inches. So you know the person is negative, below the average, negative 3.5 inches. But you don't know, the whole point is you don't know how big, is that way down here? Where is that? You don't know until you know how many standard deviations that is. Then you can visualize it on the distribution. So you have to divide by the standard deviation, and that says negative, so you say, how many standard deviations is that? How many times does 2.5 go into that? Well, it certainly goes in 1, with 1 left over. So it's 1 over 2.5, 1.4. Negative 1.4. Now you see this negative sign, and that tells you the person is below average. So this means z equals negative 1.4 means the person is 1.4 times the standard deviation below. They're below the average. That's what the negative tells you. This means below the average. Any questions on that so far? So if you're below average in anything, you're going to have a negative z-score. And if you're above average in anything, you'll have a positive z-score. And if you're smack dab in the middle, in the at the average, your z-score is going to be 0. Okay, so how about 69 inches? Same thing. Z equals 69 inches minus 63.5 inches over 2.5. So this is what? 5.5 inches above average. But in terms of standard deviations, how many of them is it? Well, it's 2 and a little more than 2. It's 2.2. That's your answer. Any questions on that? All right. Well, now we can turn the page and we can look at how the area of a normal curve is distributed. And we said already that between z equals 1 and z equals negative 1, about 68% of the area lies. What about between other z-scores? Well, we said between 2 and negative 2, about 95. Here's part of the chart. But let's look. I reproduced part of it here. Why don't we go to fill in these questions? Negative 1 and 1, negative 2 and 2. Okay, we already know this is 68%, but let's check it out and make sure. And we already know this is 95. By going to the very back of your book, to where these tables are, this sort of manila-colored off-white. And this will be the last page of your exam. It's going to be this. The very last page of your exam will be this table, so let's learn how you can use it. It's on page 337 in your books. All right, so this particular normal table gives you, let's look at what it says. Here's the z, here's the height, and here's the area. Now, we said between 1 and negative 1. So go down your z-scores until you find 1. And where is it? Right here. Okay. There it is. It's right, hold on. Okay, so I'm looking right here at 68.27, and I just rounded to 68, which is okay, that's fine. You can do that on the exam unless you're told otherwise. Now, what is this? You don't need this at all. This second column, the height at that point you don't need. We're not going to be integrating under the curve. You don't need that ever in this course. So you might as well just scratch out all your height column here, because we're not going to be using it and it could get confusing. All right, so this says that the area 1, where's the negative 1? There is no negatives on here. So you look up here and it says when z is 1, between 1 and negative z, between 1 and negative 1, this is your middle area. That's what you got. So you got 68% when it's between 1 and negative 1. That's how you read this chart. So what about if it for a z-score of 2? What about between 2 and negative 2? So you look, and there's between 2 and negative 2 is 95.45. And I just rounded down to 95 just because it's simpler. We're going to do a lot of these in our head in class. If you give a more exact answer on your exam or your homework, you will never be marked wrong. You can put that in. You can give. It's just easier for us. This is all an approximation anyway, so it's just easier for us if you don't mind rounding. So we just say 95% between 2 and negative 2. Now, when should you not round? How about when you get up to like between 3 and negative 3? Well, now look at all these. They're all 99 point, all the way from 3 all the way to 4.45. They're 99 point, well, if you started rounding at 99.5, you'd start rounding everything from 2.85 on. So that wouldn't make sense. So once you get out into the edges of the really big numbers, please keep the digits. All right. So any questions so far? So this table gives you the middle area only, but from that you can figure out any interval that you want at all. So let's go back and fill out that chart wherever we left off. Okay, so here we are. So let's just finish it up. All right, so the area between negative 0.75 and, I have to go back, I didn't look at that one. 0.75, it's not on here, is it? No. Okay, so you have to go to 0.75, and it's 54.67. Okay, so we'll just round to 55%. And this one is on here, and we're not going to round here because once you get to these high numbers, don't round. Questions? All right, now let's turn the page. And we're going to see how you can figure out any area, not just the middle area. Okay, so we're working in z-scores, and let's just quickly see how easy it is from that chart to figure out any interval. Okay, so for the following problems, draw a picture. What's the area between 0 and 1? Now, first we have to fill these in. 0, so these are marked 1, 2, 3, etc. So between 0 and 1 is what we want. So we want this area between 0 and 1. This is the area, right here. Now the chart, you look on the chart, and I hope you can remember, if you look under 1, it's going to give you not this area, but the area between negative 1 and 1, this middle area. It's going to give you this whole thing here, and this whole thing is 68%, from -1 to 1. So what do you think this must be? Because it looks symmetrical. It is symmetrical, so that has to be what? That has to be 34. So this has to be 34. And that has to be 34. So the area is just going to be half of 68%, which is 34%. Okay, what is the area greater than 1? So here we have -1, here we have 0, and here we have 1. And now we want the area greater than 1. So what do we know? Just start with what you know. Between 1 and -1 we know is what? 68%. So we're just trying to figure out that area. So how should we do it? The key fact to remember is that the entire area has to be what? The entire area has to be what? 100. So if the entire area is 100, then these two pieces together have to be what? 100 minus that, right? 100 minus, these two pieces are 100 minus 68. And we just want one of them. So 100 minus 68 is 32, so this must be 16, right? So this area right there has to be 16, which means this is 16, and they have to add up to 100. So we're saying the area of a tail, we'll take out the middle portion, and it's going to be 1/2 of 100 minus 68%, which is equal to 1/2 of 32%, which is equal to 16%. Does that make sense to everybody? Any questions on that? So that's how you would get a tail. Let's say you wanted to find out the area less than 1.5. So remember, this is 0. This is 1. That's 2. So 1.5 has to be right in between there. 1.5. Please, on your exam, mark it accurately. It has to be right there. So we want all this area less than 1.5. We don't know 1.5 off the top of our heads, so let's look up 1.5. That's the first thing you would do. You'd look up 1.5 here, and you see that it's 86.64. So let's round to 87. And 87 is between what? 1.5 and what? -1.5, which has to be right about there. There's -1 and there's -2. So now we have 87%, but that's not the answer. So what should we do? What do you think the area is? Anybody? Should we add that 87%? But now we need that piece right there. So I'm going to add what? What's the area of that? Yes, the person said, well, that's just a tail. So the two tails together are going to be 100 minus 87, right? 100 minus 87 is 13, but you're going to have to divide it by 2. So it would be plus 1/2 of 100 minus 87. So it would be 87 plus 6.5, which is 93.5%, and that looks about right. That's not the only way to do it. You could have figured out a tail first and subtracted that from 100. Same difference. Any questions? All right, now what if you're given two, from here we're given just one, one endpoint and then everything below it or everything above it, but what if you're given an interval between two endpoints here, like between 1 and 2. That's a little bit harder to do, but we can still do it. Between 1 and 2. And now that's what we want to do. So, anybody have any suggestions about how to do this one? This one's a little bit harder. Or where I should begin? It's not just a rectangle. You can't say, oh, I know the area between 0 and 2, and I'll just divide it in half. Because look, If you say, oh, I know the area between, that would be half of 95, and then I'll just divide. No, you can't divide it in half because it's a curve. This part is bigger than that. You can't do that. What do you know? You know the area between what and what? Between 1, this is 68%. What else do you know? That between -2 and between -2 and 2 is what? That whole thing is what? 95%. That's what we know. Does that help us out to find that piece? Can anybody see something from there? What'd you say?
So you can divide 95 divide by 2, and then you can use 68 divide by 2, and then subtract 95 divide by 2 minus 68 divide by 2.
Oh, okay. Yeah, okay. What he said was, do you want to, first I'll say what he said. I think this is the same thing as what you said, was that you could take 95 and subtract out this middle 68. So imagine that, right? What would that give you? If we did 95 minus 68, right there, that would give you what? Those two pieces, right? Wouldn't it? If you just, from here to here, this whole thing is 95. If you subtract out that part, 95, you're left with these two pieces, and then what do I have to do? Divide by 2. Okay, so that should do it. There's other ways too. So what do we get if we do that? We get 27 divided by 2, which is 13.5%. There's other ways to do it. Did anybody else want to suggest another way? You do whatever way feels comfortable to you. There's many ways to do this. Somebody else who had their hand up, was it the same way? Okay. Any questions on that? All right. Now, what we're going to do is put those two pieces together. What do I mean by that? The two things together, the first thing we did was change our units to z-score, and the second thing was to use the normal table to figure out, to draw a picture and figure out the area that we're concerned with. So that's called doing a normal approximation. And that's what we're going to spend some time on here. And here are the steps. And what we absolutely need is we need two pieces of information, otherwise we can't proceed. And that's the average of a set of data and the standard deviation of a set of data. And the third thing that we need to do in order for it to actually make sense and be a decent approximation is we need to know that we're dealing with a data set that does follow the normal curve fairly well. If it doesn't follow the normal curve at all, these approximations are just going to be completely off. Will have nothing to do with our picture. For example, there's a picture here. I'll show you later. It's like this. Well, that has nothing to do with the normal curve. So if we tried a normal approximation on this data, it would just be nonsense. It wouldn't be a good approximation. So you need data that's, fairly symmetrical, unimodal, like this. It doesn't have to be perfect. But then, the closer it is to this, the better your approximation. So a list of weights follows a normal curve with an average and a standard deviation. Okay, we're set. We can do that. About what percentage of the people weigh less than 115? So that's our value here. We've got our average and our standard deviation. And remember, in the normal curve, we're in standard units here. So this is going to be in z-scores, this axis. So what's dead center here? What number? 0. Okay. And this is going to be 1, 2, 3, etc. Goes on forever. All right. Now, what the question's asking us is, our real data has an axis down here that's not in z-scores, but must be in what? Pounds. And the average there is 150. So a girl who's 150 has a z-score of 0, and she would have 50% below of the people below her and 50% above. But they're asking about, I assume these are girls, they might not be, they're asking about a person who's 115. Well, that person's going to be further down. We don't know how far down. You could probably approximate it. To get to -1, we'd go down 20 pounds to 130. Another 20 pounds would take us down to 110, probably in there somewhere. But let's do it exactly. So the first step we want to do, number 1, is convert our value of 115 pounds to what? To what? To a z-score. So well, how do we do it? Z equals, and I'm just going to write it here, value minus average over SD. Okay, so there's our value. And we have to be given our average. It's 150. And here's our standard deviation. These are all in pounds. So the girl is negative, we do the subtraction, negative 35 pounds. Let's just look at that numerator. Okay, so she's 35 pounds below the average here. That's what the negative is. But until we really think of standard deviations, we don't know where she is along that curve. Until we think of, we can see that, how many standard deviations is that? So that's why we divide by 20, and we see how many times does 20 go into 35, and we get negative 1.75. That's her z-score. Now we know where to place her. This is -1, and this is -2. I made these little markings for you. So I'd say -1.7, there's negative, it's about 3/4 of the way along here. Try to do it as accurately as possible, and it's -1.75. And that's where she lines up, the person who's 115 pounds. And now you can pretty much eyeball it right here, and you see that there aren't that many people who are lighter than her. She's pretty light in this population. That's the percentage of the whole that's smaller than her. Okay? Now we want to figure that out exactly. So what do? We don't know this off the top of our head, and let's say it's on the exam. What you are going to be provided with is the table. So go to your table now and see if you can get what that answer is, what that percentage is. I'll give you a minute. Okay, look up when you're finished, when you have that, so I know people are mostly done. Okay, what are people getting for this answer? 4, that's correct. Let's see how we got that. That's correct if you got 4 here. So you look up -1.75, so you go to the back of the table, and the first thing you realize is there's no negative. But that doesn't matter, so you just go to 1.75, which is right here. And you see it's 91.99. Please round that to 92. Okay, 92, right in the middle. So you go back here between what and what? Between 1.75 and -1.75. So you say 92% between -1.75 and make it symmetrical. Here's 1, here's 2, 1.75. That's what you know. All right? How many people got that far? All right, once you get that far, you know the whole thing has to add up to 100. So these two together have to be 8. Correct? These two together have to be 8. So this has to be 4%, and that's your answer. All right. Now, what percentage of the people are between 115 and 160. Now you have two values you have to change to z-scores. Well, we've already done this one. We have to convert both 115 pounds and 160 pounds to z-scores. Well, this one to z-scores. Well, this one we've already done. What is this one? We just did it. So this is negative 1.75 from A above. So we don't have to redo this one. How about this one? We have to do this one. So what are we going to do? Z equals 160 minus what? Question? 160 minus our average, which is what? 150 divided by our standard deviation, which is 20. And that's going to be 10 over 20, which is 0.5. So there's our two z-scores. And we just want the area in between them. So here's 0. That's always in the middle. That's 150. Now we're going to go to negative 1.75 and 0.5. Do you see how it's going to be right here? If you want to draw the other axis then underneath, you can, but you don't have to. And what does the question ask us? We want the area between those two. So if we want the area between, we want all this area here. Now, how are we going to do that? What do you think's the easiest way? Any suggestions? Yes?
Find the area of the negative 1.75 divided by half, and then find the area of 0.5 and divide that half, and then half.
Excellent. I think what she said is probably the best way to proceed. What she said is, find the area between negative 1.75 and 1.75, and then divide it in half. Okay? Basically, we did that already, right here. We found the area between negative 1.75 and 1.75. We found that was 92. So she said just divide that in half, right? So this is going to be 92 divided by half. Does everybody see that? I'll do it this way. Questions on that? And then she said, find this area. And that's going to be the area between 0.5 and what? Negative 0.5 divided by 2. So fine, I'll make it look like this. She did it into two separate pieces. So we have to look up the area between 0.5 and negative 0.5 and divide it by 2. So let's do that. And I got 38 here. So we're going to divide that part by 2. Is that drawn okay? Does everybody understand that, what I did? Okay, and then she said add the two together. Okay, so we're going to add half of 92 plus half of 38, and that's 46 plus 19 is 65%. Excellent, good. That would be our answer. All right, now we're going to look at, we're going to have to go the whole time again, but you know what? We're going to complete the entire, everything you need to know for the first exam today, which means you will be able to start these. I'll post the homework as soon as I leave here. Well, maybe not as soon, maybe an hour or two, so you can get started on the homework right away and even go to the lab. And then you can also do your study guide, your practice exam, and your key to the practice exam, and there's tons more online, and you'll be all set for the exam on Tuesday. We'll have a review. Wednesday's the exam. All right, now, let's look at these last few problems, and if we focus now, you'll be set for the exam. According to our survey data, the histogram for the fastest speed ever driven is close to the normal curve, with an average of about, I just looked at it, was 91. And the standard deviation was, I'm going to round it to 20, just to make the math come out easier. Okay, now, 95% of the class listed fastest speeds between what and what? Now this 95, remember the 1, 2, 3 rule. When you see 95%, you should think that's between -2 and 2 on the normal curve. In z-scores, you should be thinking, 95% between -2 and 2. But do I want to put -2 miles per hour and 2 miles per hour here? That is ridiculous. So what we're thinking is, this is between z equals -2 and z equals 2. Now we just want to change those to speeds. So always start with the average. The average is going to be right in the middle at 91. 91. So that z equals 2 is going to be 2 standard deviations above the average. Just start with the average. I'm trying to calculate what to put in here. So you start with the average, 91. And now you're going to add to that, what do you think? 2 miles? Should it be 93? Do you think that's 2 miles? This is a z-score. It's not miles, it's not inches, it's not it's 2 standard deviations. So it's going to be 2 times whatever the standard deviation is, which is what? 20. So do you see how you're going to add 40 to 91? That's what a z-score of 2 is. So that's what you put up here. Now you do the same thing with the negative. Start at the average. But instead of adding, you have a negative. So you're going to add a -2. -2 standard deviation. So you're going to subtract 40. Subtract 40 off. So if you subtract 40 off, what do you get? And does that make sense? Don't you think in our class about 95% of the people would have driven between 50, the fastest they've driven is within those 2 limits? All right. Now, one student listed her fastest. Oh, what should I do here? Did I do this problem for the other class? Hold on. I think I skipped this because we were running out of time, and it didn't really illustrate. Let me do the same exact thing I did in the other class because it worked well. We were running out of time here. In this class, I might be able to do it, but I don't want to rush you at the end where it gets harder. This is just more of the same. Just saying what, here's giving you a speed, what percent drove less than her. Okay, so we're going to skip this for now, and I'll post it online. Now, as I mentioned before, I know it's getting long. Your brain is probably getting full. But we just have a little bit left. Okay, just a little bit left. And it goes along with what we just did. First off, if you don't have a curve, a histogram that follows the normal approximation, the normal curve, don't use a normal approximation. Look, this is nowhere near normal. So you cannot do a normal approximation. Don't use normal approximation on data that is far from normal. That's all you really need to know, and it's common sense. You'll get crazy answers. So we don't even, if you want to look at that, I'll post it and show you. You just get crazy answers then. All right, so I'll post that, but we don't have to work through it. It's just nonsense. All right, now, instead people use percentiles, and you can read that. But we also can use percentiles with the normal curve, and we can do normal approximations using percentiles. So that's what we're going to look at now. And that's the last thing we're going to do today. All right. Now, do you know what a percentile is? I mean, you know what a percent is. If you're, people get those things mixed up. If you're in the 90th percentile on some exam, That doesn't mean that you got a 90% on the exam. It doesn't mean that at all. It means that 90% of the people did lower than you. I was just looking at our final exam. Somebody was in the 38th percentile on our final exam last semester, and he got an 82. What does that mean? It means that in 82, people did pretty well, and in 82 was only 38% better than the rest of the class. All right, because that, it was just, the average was, the median was higher. So a percentile just tells you what percent of the people scored lower than you. That's all, or what percent of the people are shorter than you. So percentiles range from 0 to 100. Now, according to our survey data, the histogram for the number of hours of sleep reported students got per night is pretty close to the normal, with an average, and I rounded it here to 7 hours and made it really easy, and a standard deviation of 1 hour. Okay? Now, a student who sleeps only 5 hours per night is at what percentile? This is the same as asking, we've already done this. This isn't new yet. This is exactly the same question we've already done. It's the same as asking, what percent of the class slept less than 5 hours per night? That's exactly the same thing. So what we have to do, in fact, for all of these, it's nice to sort of have a picture of how you're going to proceed. And the very first, you start with a value, in which case it's 5 hours. And we have to change it. What's the very first thing that we have to do? We always have to change that value to what? A z-score, always. You always have to change it to a z-score. And then you draw the picture. That's this. This is how we've been doing it. So let's do it. 5 hours changed to a z-score is going to be what? Well, how are we going to change it to a z-score? We're going to subtract off what? 7 hours. And divide by what? 1. And what do we get? -2. So there's our z-score. Now we move down to the curve. And what always goes in the center? 0. And -2 is going to be down here. And what the question is asking us, this is, if you wanted to do another thing underneath, you could. This would be 7, and that's 5 in terms of hours. But you don't need to if you don't want to. And here, the question is asking what percent of the people are less than her. Percentiles, what percentile is she? And it's the same as asking what percent of the area of the curve is even smaller than her. So what would that be? Can you do that in your head now?
4.
What? 4%, almost, not, remember, you're thinking of the 92. Between -2 and 2 is what? Do you remember? 95%. Now, 5% is here, so now what do you think? 2.5, excellent. Yay! Yay. All right, 2.5%, right there. That's our answer, but also it's the 2.5th percentile. They mean identical things. That's what I want to tell you. They mean identical things. All right? And obviously somebody who was way up here at the, who slept, what would that be? 9 hours would be at what percentile? The 90 what? 7.5th percentile. All right, now we're going to go in the other direction, okay, the other direction. And I'm going to give you the position on the normal curve, the percentile, and then I'm going to ask you how much the person slept. So we're working in the opposite direction, okay? So if you start with the percentile, we're going to get, instead of this, we're going to start with the percentile, Then what do you think? You always have to go through the z, and then you're going to get to the value. That's what this one's doing. All right, so we're starting with the percentile. All right, let's do that. And let's work down here. We have the 75th percentile. That's what we know. 75th percentile. Now, what does that mean? That means, what does that mean? That means, try to think about it. It means 75% or less slept less. 75% are to the left, which means how many are to the right? It has to add up to 100%. So how many are to the right? 25%. So we want to draw two tails on here. We want to draw two tails. You always are given one. What's our one tail? Look at this. What's our one tail? This one, right? So we know one tail is 25%. We want to get a z here. This is why it's a little confusing because of our chart. We want to look up a middle area. If we look up 75%, is that a middle area? 75% is everything through here. What we're trying to do is we're trying to get a z. That's our next step. And so we have to get two tails. Otherwise, how are we going to get a z? Do you see what I'm saying? We have to get a middle area lookup. 75 is not the middle area. It's all the way there. So I know this area is 25. I know this one's 25. So do you see what I'm doing? You want to draw two tails. So here's one tail's 25. And what's my other tail have to be? So you draw two equal tails, 25. I have to split up this 75. 25 and 25, and then what's going to be my middle area then? 50. I don't know where to place it until I look it up, but this is what I want, the 50, to know how to divide that up. I need to draw two tails. And I always am going to, 75th percentile gives me one tail, one little tail, but I need a middle area there. So you look up the middle area, and the middle area of 50%, not 75. You need the middle area. So you look up z for middle area. So let's do that. So we go to the book, and we look up a z for a middle area. So you go to your middle area, and we're a 50. And you don't see 50, but it's in between 48, isn't it? Shouldn't it be in here somewhere? So you go over to your z, never use that height column, go over to your z, and it's between 0.65 and 0.7. So I would accept anything in between. Don't do 0.65 or 0.7, it's in between there. So let's say 0.68, looks a little closer to that. Okay, so it's approximately 0.68. That's our z. So now we're going to draw it in. There's 0. And now this is 0.68 and negative 0.68. That's where the 50% is. Should have been prettier and symmetrical. And the 75th percentile is all of this. You see, I had to divide this 25, I had to get a tail of 25% here, which made this be 50 in the middle. Do you understand? Does everybody understand? I couldn't do 75 because that would have been a middle. All right, so now I've got that. And now what do? Well, always start, we want this at the average. This is the easiest way to do it. You want some sleep, so start at the average. What is the average? 7. Now this tells me to what? It's positive. You add 0.68, but that's not hours, that's standard units. And I always have to say 0.68 times the standard deviation. In this case, the standard deviation is 1 hour. So our answer is 7.68 hours. Wow, you guys don't get much sleep. What would be the 25th percentile, by the way? What would be the if I asked you the 25th, could you look at this graph and give me the 25th? The 25th percentile, what would I do? I'd just have this tail, I'd draw another one, and what do you think would change? Instead of getting 0.68, what do you think I would get? What do you think I would get? Negative 0.68. Maybe we better do one more from the beginning, and I think you'll understand that. We'll do one more and you'll see it. All right. All right. This is the data from last semester. You just need to know the average and the standard deviation. What weight corresponds, all I want to know is what weight corresponds to the 30th percentile. 30th. Okay, so how am I going to do this? 30th percentile. So I start off with the 30th percentile. What does that mean? Let's write this down. You always know one tail. You do. Last time we knew the right-hand tail. You always know one tail. What tail do you think we're going to know this time? We know from here on in is 30%. So what tail do you think? In this case, what do we know? This gives you one tail. We know what? The left-hand tail. Don't we? If it's bigger than 50, we knew the right-hand tail. Here, this is easier. We know this has to be 30. Right? Correct? If it was bigger, we know the right-hand tail. In this case, we know the left-hand tail because the percentile is less than 50. If it's bigger than 50, we know this tail. All right, now what do we want to do? We want to do what? Draw how many tails? 2 tails. So draw another one. Now, what's in the middle? What has to be in the middle? We have 60 so far. What has to be the middle? Now you know your middle area, okay? So we're going from here to get our z. And what do we want to do? We look up z for middle area. Equal to what? 40%. And then we can divide things up. Okay, so let's look. 40%. And middle area 40, where is that? Okay, another one that's not great, but just estimate in there. 0.52 or 0.53, what do you want to say? 0.53? Okay, so we'll do 0.53. So we'll say approximately 0.53. So now this is 0. You know where to divide it up. At 0.53 and negative 0.53. And 30 percentile, that's a 0 in there, is this. All right, negative 0.53. That's hard to read, but that says negative 0.53. This right there. Now we want to get to our value, which is a weight, pounds. So how do we get from negative? It's very important, negative. Once you draw the picture, you would have been wrong if you didn't put the negative in. It's low, 30th percentile is low. Anything below 50th, it's going to be negative. So now you start at the average, which is what? Start at average, which is what? 134. And this tells you to subtract or add the negative. 0.53 times what? Not 0.53 pounds. What am I going to put in here? The standard deviation, which is what? What is it? 24%. 134. So you say 134 minus that. What is that? So you probably would need your calculator for this one. So you would just, oh, this is horrible. 0.53 times what? 24. So we're subtracting off, it's 134 minus 12.72. That's what we're saying. And that is what? 121.28 pounds. And that sounds about right. That girl's light. Now let's look at this next question. See how this 70 goes with 30th? So you wouldn't add up to 100. So this girl's going to be just as heavy as this girl is light. And if we did the same thing, if you saw this, you wouldn't have to do it. But 70th percentile. Now what do you know? Your right-hand curve is going to be what? 30%. So your left hand will be 30%. And your middle will be 40%. Hold on, I don't want to make you go over, but how many? 2 minutes. All right, sorry. So we just get here exactly the same thing, but now you get 0.53. So z is equal to 0.53, and your value is 134 plus 0.53 times 24. So it's 134 plus 12.72, which is 146.72 pounds. So it's the exact, these two are symmetrical. All right, now, thank you, have a great weekend. I'll send you some emails, I'll post the homework.